Hello and welcome to Principles of Mathematics, lesson number 3. In this lesson, we're going to learn about symbolic logic and the foundations of reasoning. This will serve as an introduction to these concepts. We should be able to look at some quantifiers and their effects on statements, different forms of statements, how to determine whether two statements are logically equivalent, how to develop logical arguments, and how to determine whether an argument is valid. So let's dive right in. So to begin with, what is a statement? A statement is basically a sentence that is either true or false. It cannot be both. What is the negation of a statement? Basically, a statement with the opposite truth value of a given statement. The negation of a true statement is obviously going to be false. The way we say that in mathematics, we say is if P is true, then not P is false. Usually we just read this negation symbol as not. As a really simple example, if we say that if we make the statement that 2 plus 3 equals 5, obviously that's a true statement. So if I negate that statement and I say, so this is true, so if we negate it and say 2 plus 3 does not equal to 5, that obviously would be false. On the other hand, suppose I say 2 plus 3 is 6. Now we know this is false. So if we negate that and we say 2 plus 3 does not equal to 6, notice that the negation of that false statement now becomes true. All right, so if we want to negate each of these statements, we already saw the first one. If the statement is that 2 plus 3 equals 5, obviously the negation would be 2 plus 3 does not equal to 5. If the statement states that a hexagon has 6 sides, the negation would obviously be that a hexagon does not have 6 sides. All right, simple as that. When dealing with logic, one of the things that we need to become familiar with is what is called a quantifier. Basically, quantifiers include words such as all, some, every, there exists, and no or none. Among these, some are called universal quantifiers. Why? Because they apply to every element in a given set. That includes words like all, every, or no. In other words, like no member of a set has a certain quality. That would be a universal statement about all members of that set. So those would qualify as universal qualifiers. Existential qualifiers apply to one or more, possibly all, but elements in a set. These include words such as some, there exists at least one, etc. So these are considered existential quantifiers. We will see them in action soon. All right, so let's see if we can negate each of these statements. All students like hamburgers. Notice that we have a universal quantifier here, so we're making a statement about all members of the set of all students. So to negate that, we can do it in more than one way, but one way is to say there's at least one student that does not like hamburgers, or we can say more generally, some students do not like hamburgers. All right. How about the next one? The statement says some people like mathematics. So if we're going to negate it, we should go to the extreme of saying no people like mathematics. Or to make it sound less weird, we could just say no one likes mathematics. All right. Here's an example that we're going to negate the statements in. The first one says there exists a natural number n such that 3n equals 6. Now you're going to disregard whether this is a true statement or not. Your goal is just to negate it, right? So here we can again say it in different ways, but one mathematically sound way of saying it is that for all natural numbers, n, 3n does not equal to 6. All right. Now the next statement says for all natural numbers n, 3n equals 3n. Go ahead and pause the video and see if you can negate that. All right, so remember, to negate something that's being stated for all of a class, all you have to do is say there exists a natural number n such that this doesn't hold. In other words, 3n does not equal to 3n. All right. Again, we're not worried about the truth or falsehood of the original statement. We're just trying to learn the act of negation. Otherwise, if you look at the first statement, there exists a natural number n such that 3n equals 6. That's actually a true statement because we know that number very well as well. What is the number that you have to multiply 3 by to get 6? Of course, that's 2. So the first is a true statement. So what does that tell you about the negation? The negation is false. How about this one? Is this a true statement? All we're saying is you take any natural number n and 3 times that number equals 3 times that number. Of course, that's true for every natural number, right? So again, we have a true statement, original statement, and the negation we wrote is of course false. But we weren't worried about that. We just wanted to learn how to negate. All right, so when it comes to logic, one of the most useful tools at our disposal is what's called a truth table. It's a symbolic system, basically using a table that shows all the possible true-false patterns for the statements. Now, here's the truth table for negation. So what you do is you write a statement such as P, right? P could be any statement at all. And what are the possible values for P? Think about it. Remember, in mathematics and logic, a statement is either true or false, not both, right? So the possible values for P are truth values are true or false, right? So the negation, not P, is of course going to have the opposite value at each step. So if P is true, not P is going to be false. And if P is false, then not P is going to be true. So here's an example of a truth table for negation. A conjunction is basically an AND statement. Any compound statement created from two given statements using the connective AND is called a conjunction. we use the symbol of the upper caret like that to represent and a conjunction is true only if both statements are true. Otherwise, it's false. In other words, we make our truth tables in the following way. Because we have two statements here, we're going to see what happens if they're both true. What if the first one is true, the second one is false? What if the first is false and the second is true? And what if they're both false? This covers all the possibilities for two statements, right? They're either both true or both false, or one is true and the other is false, right? So now when it comes to an AND statement, the bar for being true is very high. In other words, an AND statement is only going to be true if both of the original statements are true. In every other case, it's false, right? So if you look at some simple examples, you'll see why this is true. For example, on this one, let's say the first statement, the P is, for example, a simple statement like 2 plus 3 is 5, right? And I put the connector and I say, and 3 plus 4 is 8. Now, obviously, we know that this one is true, right? But this one is false. So as an AND statement, the whole statement becomes false. All right. The same can be used here. And of course, if they're both false, the conjunction is also false, right? So remember, a conjunction is only true if both statements are true. In all other cases, a conjunction becomes false. This very much has to do with the regular interpretation of what and means in English, right? When we say one thing and another, then we expect both to be true in order for the conjunction to become true. Now, a disjunction, which is an or statement, behaves very differently. We use the right side up, or actually, but this would be an upside down caret, right? To represent a disjunction. And in exactly the opposite way to how a conjunction works, a disjunction is only false if both statements are false. Because as long as one of them is true, because you're saying either, for example, let's go back to the example we were using for this row, right? We said 2 plus 3 equals 5, or 3 plus 4 equals 8. Well, notice this is true, this is false. But as an or statement, I'm saying, hey, either this is true or this, right? So because it's an or statement, as a disjunction, the whole thing becomes true. Now, notice that a disjunction is only false if both statements are false. So if you say 2 plus 3 equals 6 or 3 plus 4 equals 8, well, you're dealing with a false or a false, so therefore the disjunction itself becomes false. So you make sure that you understand how different these are. I'll put them next to each other again for you to compare. Okay, now we can see them side to side. So remember, an or statement is only false if both statements are false, whereas an and statement is only true if both statements are true. In all other cases, an and statement is false, and for an or statement, only false if both statements are false, and true in all other cases. Okay, I want you to take a minute, pause the video, and see if you can classify each of the following as true or false, where these are the statements. P is the statement that 2 plus 3 equals 5. Q is the statement that 2 times 3 equals 6. And R is the statement that 5 plus 3 equals 9. Now, I've put the tables for negation, conjunction, and disjunction here to help you remember which way to go. So take a minute to do that and then come back. All right. So the first thing we should do here is, first of all, go ahead and determine the truth or falsehood of each of the statements. So let's look at P. 2 plus 3 equals 5. Is that true or is it false? Well, as you can see, that's a true statement. So P is true. How about Q? 2 times 3 equals 6. We notice that that's also true. And R, 5 plus 3 equals 9. We know that R is false. Now, how about P and Q? That's a disjunction, a conjunction, right? An and statement. We know an and statement is true if both statements are true. So therefore, since both P and Q are true, A is going to be true. How about Q or R? That's a disjunction. And we know that as long as one of the two statements is true, a disjunction is going to be true. The only time a disjunction is false is if both statements are false. And here we can see that one is true, the other is false. So therefore, as a disjunction, Q or R is going to be true. How about not P and or R? That's a disjunction or. So not P. Now we know that P is true, right? So what is not P going to be? That's going to be false. Now we know that R is also false. So we know that when both statements are false, a disjunction in fact becomes false. All right, so that's how you handle statements like that. All right, compound statements of that type. All right, so think about this for a minute. Make sure it makes sense before we proceed. All right, here are a few more examples based on the same statements, right? So again, remember that P is true, Q is true, and R is false. All right, so not P and not Q. Now, what do we know about P? P is true. So what's not P going to be? False. And what is not Q going to be? That's also going to be false. So we basically have false and false. So we know that a conjunction or an and statement is only true if both statements are true. So since these are both false, the conjunction is going to be false. Now, here we're looking at the opposite of this conjunction. So first we're going to figure out the conjunction, then we'll negate it, okay? Now, we know that P is true and Q is true. So P and Q, because they're both true, is going to be true. So we're looking at the opposite of a true statement. So that's going to be what? False. All right, because remember, P and Q is true. So what is the negation of a true statement? A false statement. All right, so now here we're looking at P and Q, or the opposite of R. Now, we know P and Q is what? P and Q is true. Why? Because P and Q are both true. So we have true or. Now, we know that R is false, right? So what is the negation of a false statement going to be? That's going to be true. So here we're dealing with a true or true scenario, right? And of course, we know that true or true is always true. So this one is going to be true. It's very, very simple. You just have to get used to it. You know, if you've never seen truth tables or symbolic logic, it takes a little bit of getting used to, but it's all really straightforward and not to be um, too obvious, but logical. All right, let's go ahead and move on. All right, next we want to look at conditionals and biconditional. A conditional, or it's also called an implication, is a statement expressed in the form of if P, then Q. Another way of saying it is that P implies Q. Same thing. So if you say if P, then Q, or if you say P implies Q, you're basically saying the same thing. In a conditional or implication, the P part is the if part. In other words, the P plays the role of the hypothesis, and the then part, the Q part, becomes the conclusion. So hypothesis, conclusion. Now, the truth table for a conditional is given here. And notice that a conditional is similar to a disjunction, right? In fact, later we will show that it is in fact logically equivalent to a particular disjunction, which we'll see later. And because of that, it behaves very much like a disjunction as well. Notice that the only time a conditional is false is if the hypothesis is true and the conclusion is false. In other words, if a truth is implying a falsehood, okay? That's the only time a conditional becomes false. Otherwise, true implies true is true. False implies true is true. This is one that confuses people. Basically, think of it as anything follows a false hypothesis, right? So this one is true. Again, this will make more sense to you once you understand what disjunction this is equivalent to. And false implies false is also true. So make sure you understand and remember the truth table for conditionals. We'll be using it later on. Anytime we're looking at an implication like P implies Q, there are three related implication statements which have special names. So the statement itself, the original statement, is P implies Q. The converse of that is when you write Q implies P. In other words, you switch the roles of P and Q. The inverse is not P implies not Q, and the contrapositive is not Q implies not P. See? So, as it turns out, we're going to establish very soon that these two statements are actually equivalent. We will also see that these two are also equivalent, just because if you notice, this is also the contrapositive of that. So a statement and its contrapositive are logically equivalent. We'll learn about how to show that very soon. So here we want to get a little bit of practice with these new concepts. So we want to write the converse, inverse, and contrapositive of this statement. If I am in San Francisco, then I am in California. All right. So let's think of that as the P, and the I am in California part becomes Q, right? So to write the converse, we know that we have to say Q implies P, or if Q, then P, right? Remember, Q implies P is the same thing as saying if Q, then P. So all we have to do is switch it up, right? So here we're going to say if I am in California, then P, I am in San Francisco. All right. For the inverse, we know that the inverse of P implies Q. The original statement, of course, itself is P. Let me not use an arrow, that could get confusing here. So P implies Q is the original statement, right? So we know that the inverse of P implies Q is not P implies not Q. So what is not P? Well, P is if I am in San Francisco. So again, I want you to pause, think about this, and come back. Anytime you feel like, oh, I should be able to do this, you should do that without me saying it. But I'm going to keep reminding you just to help you out. So if not P, right? So we want to say not P, then not Q. So not P here becomes what? If I am not in San Francisco. Actually, let me just be lazy here. If I'm not in SF, then not Q. Q is I'm in California. So what's not Q going to be? I'm not in California. All right. So how about the contrapositive? If not Q, then not P, right? So what is not Q? Well, here's Q. I am in California. So not Q becomes I am not in California. So if I am not in California, then not P. P is, of course, I am in San Francisco, so not P becomes I'm not in San Francisco. All right. So that is how you do these implications given P implies Q. Now, as far as the truth is concerned, of course, we know that the original statement, if I am in San Francisco, then I am in California, is true, right? The converse, think about it. If I am in California, then I am in San Francisco. Is that true? Well, if it's true, all of us in Los Angeles are in trouble because we're in California, but we're not in San Francisco. So this one turns out not to be true. How about the inverse? If I'm not in San Francisco, then I'm not in California, right? Um, well, think about it. Is that true or not? Again, that's not true, right? Because you may not be in San Francisco, but still be in what? Be in California. How about this one? If I am not in California, then I'm not in San Francisco. All right, well, you have to be a little bit careful here because there are actually 4 San Franciscos in the United States, I believe, at least, here, but there are more across the world as well. So, but let's for a minute assume that we're talking about the San Francisco, right? The one and only, the big apple, right? So if we're only focused on that one San Francisco in this statement, then notice that this would also become true, right? So we have to have the caveat that we're only dealing with this particular San Francisco. And if that's the case, then this statement becomes true. So if a statement is true, its contrapositive is also going to be true. All right, and we'll see that again in using truth tables in a minute. Okay, we're finally ready to go ahead and do a proof using truth tables. And this is a simple, beautiful, and very powerful idea. So we want to show that P implies Q, or if P then Q, is equivalent to saying not Q implies not P. This symbol here with the three lines has to do with logical equivalence. That means whether you say one or the other, you're basically saying the same thing. The implication is the same. All right, so here we're just going to start out by putting all possible truth values that P and Q can have, right? That's where we always start. So we know that they can both be true. We'll do the extremes first, right? Or they can both be false, or one can be true and the other false. Either P can be true, Q false, or P can be false and Q true, okay? Starting with that, then it's easy to proceed, because if I want not P, I'm just going to take the opposite of every value that there is for P. So when P is true, not P is going to be false. When, again, here P is true, so that's going to be false. Here we have P is false, so not P is going to be true. And here again, P is false, so not P is also going to be true. Now, for not Q, you're only going to look at this column now and just take the opposite of each of these and put it in here, right? So if Q is true, not Q is going to be what? False. And if Q is false, then not Q is going to be true. If Q is true, not Q is going to be false. And if Q is false, then not Q is going to be true. All right, now P implies Q. So now we're only focused on these two and going in this direction, right? So let's bring back the table for implications just to remind you, okay? Okay, so I've pasted the original table we had, the truth table for implication. So remember, an implication is only false if the hypothesis is true and the conclusion is false. That's the only time an implication becomes false. So true implies true. We know that is true. True implies false. We know that is false. It's the only time an implication is false. False implies true. We know that's going to be true. And false implies false. That's also true. Now, let's look at not Q implying not P. So remember, you're going in this direction now. This direction. Not Q implying not P, right? We want to see the truth value for this. So false implies false. We know that's true. True implies false. We know that's the only case in which an implication becomes false. So this is false. false implies true. We know that's true with implications, and true implies true becomes true as well. Now, you notice how the truth values for P implies Q and not Q implies not P. In other words, it's contrapositive. Remember, not Q implies not P is the contrapositive of P implies Q. Notice these values are identical. This is how you prove logically that two statements are what we call equivalent, because their truth table values are identical. And that's how it's done. So make sure you understand this simple but very important example. Take as much time as you need before we proceed. All right, next we have the concept of a biconditional. Basically, if you have P implies Q and Q implies P, the way we say it, we write that is we write P with a double arrow and then Q. And the way we read it, we say P if and only if Q. In other words, the two statements P and Q then become equivalent. Let's look at the truth table for this scenario. So first we'll look at P implies Q. Notice that true implies true is true, true implies false is false. The only time an implication is false. False implies true is true, and false implies false is true, sorry. Remember, the only time an implication is false is if the hypothesis is true and the conclusion is false. So false implies false is actually true. All right, now Q implies P. So now we're looking in this direction, right? True implies true, true. False implies true, true. True implies false is our only false case because this is true, the hypothesis is true, and the conclusion is false. Looking from right to left, right? So this is false, and false implies false is true. Now we want the conjunction of those. Remember, P, in other words, up here, instead of writing this, we could have written P if and only if Q, right? So if you take the conjunction of these two, remember conjunction is only true if both are true, right? So true and true, true. False and true, false. True and false, false. True and true, true. So that is how you find the truth table for a biconditional. A biconditional is true only if both P and Q are true, or P and Q are both false. Otherwise, the biconditional becomes false, which makes sense, right? Because if they're both false as well, one implies the other, the second implies the first. So that also becomes true. So in these two situations, when they're both true or both false, the biconditional becomes true, and in the other situations, it becomes false. So here is the truth table for a biconditional. Okay, so now we can bring these concepts together in what is called valid reasoning. And this kind of reasoning is also, which is summarized in these three statements, is also called a modus ponens. Okay, You may have heard of that before, and this is what it is. In other words, here we say if P then Q, right? Now imagine that we know that P is true, right? So this kind of reasoning says, oh, therefore Q must be true as well, okay? So we know that P implies, the symbolic way of writing this is the following. We say P implies Q, and then the second statement is just P, okay? And then therefore the final statement is Q. That's it. That's the symbolic way of writing this. All right, in other words, if P implies Q, and if you have P, then you also have Q. All right, here's an example. All cats like fish. Now, Felix happens to be a cat, right? What can we conclude? Then for Felix must like what? Fish. That's a example of a valid reasoning or a modus ponens. One way we can represent this is using what's called an Euler diagram. Euler is one of those mathematical giants whose, you know, uh, basically fingerprints are all over mathematics. Notice that in this kind of a diagram, what you represent the different classes is with these circles, right? So in the largest circle, we have all creatures that like fish, basically, right? Now, as a subgroup of these creatures, we know we have our good old cats, right? The felines. Now, and within that group of subgroup, we know that we have a certain individual called what? Felix. Therefore, you can see how this reasoning works out, because if Felix is part of this group, then it also must be part of what? That group. So that's how you can use an Euler diagram to represent this kind of reasoning. All right, let's see if we can use an Euler diagram to determine if this argument is valid. The hypothesis is that in Washington, D.C., all lobbyists have influence. We also know that no one in Washington, D.C. over 6 feet tall has influence. We want to see if the conclusion that persons over 6 feet tall are not lobbyists in Washington, D.C. is a valid conclusion. So here's what we can do. We can start by basically using a rectangle like this to show all of Washington, D.C. Now, within Washington, D.C., we know we have this group of influential people. So we'll draw a large circular kind of object, not quite a pretty one, but we'll let that represent the people in Washington, D.C. that have influence. And we know that all the lobbyists fall in that region because they all have influence, right? So within here, we have the group of people who are lobbyists. Now, remember, this tells you that it's not necessary that all influential people are lobbyists, right? There may be influential people who are not lobbyists. That's why this circle is larger than that one, or oval, whatever. Now, however, we know that no one in Washington, D.C. over 6 feet tall has influence. So the people who are over 6 feet tall are going to be completely outside of the influential circle, right? So let's do another little circle here, or a circle-like object here, and we'll call this one the taller than 6 feet individuals, right? So does it kind of logically follow that the people over 6 feet tall are not lobbyists. As you can see clearly from this diagram, that's a valid argument, because if you're over 6 feet tall, you're not even within the influential circle to be able to be considered. And if you're a lobbyist, you're contained completely within that. So these two sets, the set of lobbyists and the set of people greater than 6 feet tall, have no points in common. Therefore, this argument would be valid. All right, so I think that's enough logic for one day. We'll call it quits there, and as usual, we'll just go ahead and take a look at some of the problems from homework, which could be benefiting from some hints. So let's go and take a look at that now. All right, this first one we're going to look at is an important one because it is actually showing something that I indicated earlier, but we haven't proven yet. I told you earlier that if you look at the truth table for an implication, it looks very similar to the truth table for an disjunction. And I said because, as it turns out, an implication is equivalent to a disjunction. So this is actually the disjunction that P implies Q is equivalent to, not P or Q. Now, let's go ahead and bring back the truth tables for implication and disjunction, not this particular disjunction, but disjunction in general, to show you what I'm referring to. Okay, so here you can see the truth table for a disjunction and for one for an implication. And when I first showed you the implication, I told you it looks somewhat like that of a disjunction because it's true in all cases except one, right? So they share that in common. But obviously, these two are not logically equivalent. An implication P implies Q is not logically equivalent to P or Q. However, if you take a look at negative P or Q, you're going to see a different result. So we go ahead and proceed as usual. And notice that we as always, we start with the values for P and Q. They did that for us here. So we go ahead and complete the rest of the table. So we know that true implies true is true. True implies false is false. The only time a conditional is false. False implies true is true. And false implies false is also true. Now, the negation of P, wherever you see P, use the opposite value here. So if it's true, not P is going to be false. And if it's true again, it's going to be false. And in these two spots, it's false, so its opposite is they're going to be true. So now we want to look at not P or Q. So you're focused on the second and the fourth columns, right? So remember, this is a disjunction, which is only false if they're both false. So looking at the second column and the fourth column, where is it that they're both false? Only here, right? In all other cases, one is true, the other is false. One is true, or they're both true, or one is true and the other is false. So the only time that not P or Q are both going to be false is right here. So we get a false here and true everywhere else. Now compare this column with that column. Notice what they are. They're identical. Remember what that means? That means these two statements are logically equivalent. So we can write P implies Q, remember 3 bars, is logically equivalent to not P or Q. All right. Now that we have that, the other parts you should be able to figure out. So I just wanted to tell you about this really important logical equivalence, which explains, for example, why uh, some of the harder to absorb things with respect to implication happen to be true, like false implies false is true, etc. So it's because of this implication with an or statement that those now start to make sense. All right, that's that. All right, here's a truth table, which is not difficult to obtain. I just want to give you a hint about how to deal when these parentheses situation comes up with these negations. So if you have a situation like this, you're always going to want to figure out the inside of the parentheses first. In other words, you first figure out P implies Q, then all you have to do is negate each of these and you get the final result. All right, looking at these, we're trying to determine if each one is a statement, and if it is, then whether it's true or false, right? So the first case is pretty simple. Tennessee is a state. That is obviously a statement and true. The second one, run to the store. Well, that's not really a statement. That's a command, right? So uh, it's impossible to determine whether it's true or false. So it's not a statement. Here's another one, and this could be confusing to some people because we often say that when you want to, when we first teach students about expressions and equations, we always say that make sure if you're going to translate an equation into plain English that it turns out to be a full sentence, right? So yes, in that sense, it's a statement because it can be written as a full sentence, but the reason that from a logical point of view in this discussion, this is not considered a statement is the fact that we can't determine whether it's true or false. So because of that, we don't consider this to be a statement. This one, of course, is a statement because we can determine its truth or falsehood, and obviously it is false because 3 plus 1 is not 8. Here we have an important rule from logic called De Morgan's law, and it states that the negation of this conjunction, so not x and not y, is the equivalent of x or y. Now, you can actually prove this using a truth table. Let's see how you would go about doing that. Well, we can start by making our table. We're going to need x, we're going to need y, we're going to need not x, we're going to need not y. Why? Because we need to form the conjunction not x and not y. And we need the negation of that. So not x and not y. And finally, we also need to have x or y so that we can compare these two, see if they're logically equivalent. Okay, so this is how you go about proving a logical equivalence using truth tables, right? So with x and y, remember, here we go again. I'll be right back. All right, so with x or y, it's just like p and q. So we start with the possible values for them. You know, they can both be true, or we can have first one be true, second one be false, first one false, second one true, and or we could have both false. Okay, so those are all the possibilities there. Let's try to keep these kind of clean. All right, so now we're going to look at not x. So remember, if x is true, not x is going to be false. Here again we have x is true, so false for not x. F, so if x is false, not x is going to be true. Again, if x is false, not x is going to be true. Now, we're going to look at not y. So if y is true, we know that not y is going to be false. If it's false, then not y is going to be true. If it's true, not y is going to be false. And if it's false, not y is going to be true. So now we want to look at the conjunction of not x and not y. In other words, the conjunction of these two. Remember, a conjunction is only true if they're both true, false in all other cases. So we can see that the only time they're both true is right here, and that's when the conjunction is going to be true. And for all the other cases, because at least one is false, they're going to be false. All right, now we're going to look at the negation of this whole conjunction right here. So that just means whatever values these are going to be the exact opposite, right? So false, the opposite of false will be true. The negation of false will be true again, and then true again. And for the negation of true, we're going to get false. Now we want to look at x or y, right? So we go back here. Remember, a disjunction is only false if they're both false. So the only place this disjunction here is going to be false is right here. So down here, we're going to get false. In all other cases, it's going to be what? True, because at least one is true. So, and now you can see not x and not y is logically equivalent to x or y. Why? Because their truth table values are identical. All right, that's how you do a logical proof using truth tables. All right, so here's an interesting problem. It states that a statement and its converse are both true. That's the assumption. If a statement and its converse are both true, which of the other forms, inverse and contrapositive, are also true? Okay, so this goes back to understanding all four of these concepts. So if the statement itself is P implies Q. Now, there's a little technical issue with this, the way this problem is written. What they mean is, instead of a statement, they actually mean if a conditional, okay, and its converse are both true. So we kind of know what they mean, so we'll go ahead and proceed. So this is the statement itself. We know that the converse of P implies Q is Q implies P. Now, the inverse is going to be not P implies not Q. That's just by definition of inverse. And the contrapositive is going to be not Q implies not P. Now, we've already seen that these two are logically equivalent and that these two are logically equivalent. Okay? So if this one is true and this one is true, because these two are logically equivalent, that means this is going to be true. And because these two are logically equivalent, it implies that this one is going to be true. So if a conditional and its converse are both true, then both the inverse and contrapositive are also going to be true. So it's a nice problem because it really forces you to understand this concept of a statement, its converse, its inverse, and its contrapositive. All right. All right, I think that's where we're going to call it the day. And I think that we've done enough for you to be able to handle the homework now. So with that, I ask you to take care, and I will see you at the next lecture.